Alrighty, hopefully that made sense for you. Let's now move on to another sample problem. An iron ore was analyzed by dissolving a 1.1324 gram sample in concentrated hydrochloric acid. The resulting solution was diluted with water, and the trivalent iron was precipitated as the hydrous oxide Fe2O3 with some amount of water by addition of ammonia. After filtration and washing, the residue was ignited at a high temperature to give 0.5394 grams of pure iron 3 oxide. Calculate A, the percentage of iron, and B, the percentage of iron 2 and 3 oxide in the sample. This should have a similar logic as the first problem. It might seem more daunting because there are now a lot of big words and big chemicals, but it should still be the same thing. Let me start by writing down the given. I know that I'm starting with 1.1324 grams of sample. I know that the sample was processed to precipitate this variable chemical formula. Since the chemical formula of the precipitate is not exact, we're not really sure how many equivalent amounts of water there are. We cannot accurately use this solid because the mass would differ for a value of x. Again, we have no means of knowing of what x is right now. So instead, we convert this solid into the more inert and more consistent iron 3 oxide. That's 0.5394 grams of iron 3 oxide. Converting the given into this flowchart form, it suddenly makes it seem so simple, doesn't it? We're required to calculate for two values. That's the percentage of iron and the percentage of iron 2,3 oxide. I say iron 2,3 because if you notice, the oxidation number of iron in this chemical formula is, if this is minus 8, this is plus 8 over 3. A fractional oxidation number means that it is composed of more than one oxidation state. In this case, if we have both iron 2 oxide and iron 3 oxide, we can summarize all of the iron oxide in terms of iron 2,3 oxide, which has a fractional oxidation number. Anyway, let's not dwell too much into that. Let's try solving the problem. Let me write down first the molar masses. Iron, 55.847. Iron 2,3 oxide, 231.54. And that's all she wrote. Let's give it a go. Let's start with A. Percentage of iron. If the type of percentage is not specified, provide the percentage which makes sense. In this case, we're dealing with grams. So this percentage should be percentage by weight. Percentage by weight is grams of analyte over grams of sample. So the denominator is 1.1324 grams. How do we get the grams of iron? Let's start again from the bottom and then move upwards. If we have 0.5394 grams of iron 3 oxide, I know that is, I forgot to write it down, 159.69 grams per mole. So I can convert this into moles. 1 159.69 grams, 1 mole of iron 3 oxide. Again, I want grams of iron, so I need to convert the moles of this structure into moles of iron. Notice that for every mole of this chemical, there are 2 moles of iron. So, I need to specify that. And at this point, it's just conversion into grams. Now we have grams of iron. If you're not sure, make sure to double check that all the units cancel out. We only now have grams of iron left in the numerator. Since we now have grams of analyte, we just need to divide 1.1324. So we're done with this step. We didn't have to do anything on this step. And we are now doing this step. So that's 1.1324 grams. And let's just multiply everything by 100%. I'm running out of space, so let me write it like this. Calculating for this value should give us 33.32% of iron. That's 4 significant digits based on the given. Easy, right? B should also not be too far off. If we're asked for iron 2,3 oxide, we're still gonna start with the same thing. That's 0.5394 grams. Iron 3 oxide, 159.69 grams per mole of iron 3 oxide. What's difficult now here is converting the moles of iron 3 oxide to the moles of iron 2,3 oxide. Now, to solve this problem, we need to look at the analyte. Again, the analyte in this case is iron. So we only need to really ensure that iron checks out. Oxygen can be conveniently ignored because it came from the atmosphere anyway. If our analyte is iron, we only need to balance the iron. So you could imagine that if there are 3 moles of Fe2O3, we have 2 moles of Fe3O4 because in both cases, that's 6 moles of iron. I hope that makes sense to you. Again, if we have 3 moles of Fe2O3, which is 6 moles of Fe, that is equivalent to 2 moles of Fe3O4 because that is also 6 moles of Fe. Let me write it down for you. 2 times 3 is 6 moles of iron. In the same vein, 3 times 2 is also 6 moles of iron. Since we now have moles of Fe3O4 or iron 2,3 oxide, we can just convert that into grams. It's 231.54 grams per 1 mole. Oops. And we should just put in the 100% here. Dividing everything by 1.1324 grams. Let's calculate for the final value. That's 46.04% of iron 2,3 oxide. Were you able to follow with my calculations? If not, don't worry. Please work through this video again more slowly so you can work and understand it at your own pace. But notice that for both the first problem and the second problem, and the two steps in the second problem, all of my calculation can be constructed in one expression only. Don't be afraid of gravimetry. There might be a lot of conversions involved, but it's just very basic algebra. All you need to do really is to figure out the stoichiometry. In this case, the bulk of the expression would be conversions, and you should be ready to go. In the next example, we will look into a more algebra-intensive problem. So if you haven't really grasped the concepts introduced in these two problems, I highly suggest you take your time and really get into the details as to why the solutions were constructed as such. Again, there is no rush. Gravimetry really takes some time to understand, but once you get it, it should be smooth sailing. I'll see you in the next example where I will show you how to solve a more complicated gravimetry problem.